Very good morning to everybody. Welcome to the sixth session of classical mechanics. In the last session, we have derived Lagrangian equation using D'Alembert's principle. In this session, we use Lagrangian equations for constrained motion. The application of Lagrangian equation to simple pendulum. So in the last class, we have derived Lagrangian equation, where the Lagrangian equation of motion is d by dt of dou L by dou Q dot J minus dou L by dou Qj is equal to Qi, which is a generalized form of Lagrangian equation. For a conservative force, Qi is equal to 0. Then the Lagrangian equation of a motion becomes d by dt of dou L by dou Q dot minus dou L by dou Q dot J is equal to 0. So the main objectives of this session is to understand how kinetic and potential energies are derived for a constrained motion and applying Lagrangian equation for simple pendulum. By the end of this session, you will be able to solve Lagrangian equation for simple pendulum. Let us consider a body of mass m, a bob, attached to an inextensible wire of length L. Let the pendulum is suspended in its mean position. Then the bob is moved to its extreme position and allowed to oscillate. We find that the simple pendulum is constrained to move in a plane with x and y. In a plane polar coordinates r, theta with the coordinates required to specify simple pendulum. However, r is a fixed, whereas angle theta is changing from its mean position to the extreme position. So the angle theta between the rest position and deflected position is chosen as generalized coordinate. So the kinetic energy of the bob is given by T is equal to of m L square theta dot square. The potential energy of simple pendulum V is equal to mgh, which is nothing but mgl into 1 minus cos theta. So we have obtained the kinetic energy and potential energy of simple pendulum. The Lagrangian equation, we know that L is equal to T minus V. Substituting T and V terms, we obtain Lagrangian term, which is equal to L is equal to of m L square theta dot square minus mgl into 1 minus cos theta. Here we observe that theta dot and theta So the Lagrangian is a function of theta, theta dot and t. So theta is chosen as generalized coordinate. On differentiating L term with respect to theta dot, we obtain m L square theta dot. Similarly, differentiating L with respect to theta, we obtain we obtain minus mgl sine theta. Substituting dou L by dou theta dot and dou L by dou theta in Lagrangian equation, we obtain theta double dot plus g by L sine theta is equal to 0, which is the required equation for simple pendulum. Note that if the amplitude of the motion of a simple pendulum is very small, sine theta is approximately equal to theta. Then the above equation reduces to theta double dot plus g by L into theta is equal to 0, which is also an equation of the motion for small amplitude. So in this session, we have derived kinetic and potential energy of simple pendulum, and we have used Lagrangian equation to obtain the equation of motion for simple pendulum. Let's have a small MCQs for the session. Question number 1. The coordinate chosen for generalized coordinate in simple pendulum is option A R, option B L, option C theta, option D none of the above. So we know that in simple pendulum the generalized coordinate is theta. So the answer is C. Question number 2. The potential energy in the simple pendulum is given by option A mgh, option B mgl into 1 minus cos theta, option C mgl, option D none of the above. So we know that the potential energy in a simple pendulum is given by mgl into 1 minus cos theta. So the answer is option B. Question number 3. The equation of a simple pendulum is theta double dot plus g by L theta is equal to 0. Option B, theta double dot plus g by L sine theta is equal to 0. Option C, mgl sine theta. Option D, none of the above. So the option is B. Thank you. Thank you. So the sources: Classical Mechanics by Goldstein, Classical Mechanics by Gupta, Kumar and Sharma, Classical Mechanics by Takwala and Puranik, Classical Mechanics by J.C. Upadhyay. Thank you.